Hello and welcome to All Space Considered, everyone. I'm Dr. David Reitzel, and with me tonight is Laura May Abram, Ginger Rose Brucker, and Jared Head. And we also have a very special guest with us tonight that we'll get to when I go through the program, but I can't wait for it. We've got a terrific program for you. All Space Considered, as always, is brought to you by Griffith Observatory, the Department of Recreation and Parks of the City of Los Angeles. And we always like to thank Griffith Observatory Foundation, who is our exclusive nonprofit partner. So thanks to all the foundation members out there and to everybody that's made a donation that supports all of our programming. Well, tonight on All Space Considered, it is Thursday, November 20th, 2025, and thanks to the crowd here tonight that braved the rain in Los Angeles. We have a rainy night, but we've got a good crowd here. So thank you all for coming out for All Space Considered. Also, those of you at home, we thank you too. And tonight we're going to talk about auroras across America. How many of you in the audience have seen the Aurora Borealis, and did anybody catch this last one? A couple of folks did. Terrific. We're going to show you some pictures and explain where those come from. And then we're going to do some space news shorts, just a couple of short stories to show you that there's other space news going on. Then we're going to do Hurricane Melissa, which was our mostest this month. Then Jared will show us some out to launch. We've got some amazing footage of the New Glenn 2 launch, as well as a couple other things that went on. So space has been a busy place this last month. Then we'll do some pretty pictures with Ginger. And then, like I said, we've got Dr. Bryce Bolin as our special guest tonight, talking about interstellar objects and comets. And indeed, there's one flying right through our solar system right now, 3I Atlas. And he's going to tell us about those objects, about his studies of them, and how 3I Atlas fits into it all, or at least I'm going to ask him that question if he doesn't get to that. So we're looking forward to that segment of our show tonight. Well, to kick things off, this background image of our show, Ginger, this is actually an image you took. So why don't you explain what this is all about?
Yeah, absolutely. So I had the pleasure of capturing the total solar eclipse back in April of 2024. And this is my image here. And the reason I wasn't here last show was because I actually was up in San Francisco showing this piece to the San Francisco Fall Show, and it was actually featured in a art gallery with 23 women contemporary artists. And so here I am holding a small postcard size of the actual eclipse photo, and I thought it would be fun to show this little video that they got. So here you go.
Oh, was it on the docks, that kind of area?
Yeah, so Fort Mason area in San Francisco.
San Francisco Fall Show. We are showing an exhibition of sculpture, painting, photography, works on paper, and collectible design by contemporary women artists. Please join me. This amazing piece is by Ginger Rose Brucker. In addition to being a beautiful harpist, Ginger Rose is an astrophotographer, and she took this photo with her telescopic camera of the eclipse. This is literally a photo of the eclipse. And we printed it on glass with this mirror backing, and it's glorious. It's been very, very popular at the show.
Yeah, so
it's pretty rare for art shows, I feel, to have astrophotography.
Yeah.
This is a pretty nice...
Maybe you're trailblazing here, Ginger.
Well, you know, it was
more
pretty...
astrophotography and
yeah, it was pretty neat to have it as well on just like a reflective surface like that with a mirror backing, so you could actually see, you know, that diamond part of the eclipse, the diamond ring, exactly. And so this next photo is all of us. Laura May led the trip to Arkansas, where we were in the path of totality. And so we are set up here with our cameras and our telescopes.
And not many people had a sky like this.
That's right.
Originally, we were meant to be down near San Antonio. And then the weather forecasts the week prior looked a little dire, and so
I mean, we were literally, we were chasing the eclipse.
The foundation trip I was on, we were in Texas, and we were told, well, you can't chase because you've got a whole group of people with you, and it's not safe. And the skies luckily cleared for us, and we managed to see it, but a lot of folks nearby did not. So this is not the sky I had.
No, it's great. We had a nice opening. Here we are, Laura May. You're set up there, and then I think you have your lent over there as well. that was the whole entire group of everybody, so pretty fun.
Great site.
Lots of
for an eclipse
photography
there.
and footage and things
Exactly.
that came out of it, which was great.
These are just some of the sacrifices one has to make. Okay, we had blankets for the cameras, using to shade ourselves and our equipment during the eclipse.
Sacrifice of a nice grassy field and
I know.
trees
It's a
and
Life
dog
wildlife.
eat dog world out
Yeah,
there.
it looks
Yeah.
rough.
I feel like eclipse chasing is not always this nice.
No, and of course,
Well, it is a very social activity, though, and that's what these pictures really demonstrate, is folks get together to experience the eclipse, and you have a lot of fun, you hang out with folks, but then when the eclipse hits, it is life-changing. If you've
Yeah.
never seen one before, you need to get out and see a total solar eclipse.
course.
And partial isn't good enough.
Yeah,
it's like
the
somebody
same.
telling you what chocolate cake tastes like and actually eating chocolate cake. It is
Right.
that different from a 99% to 100%. It's completely a different experience.
yep.
So-
And here I am with the eclipse glasses. Just disclaimer: make sure you have protective eyewear. This was during the totality, which was 4 minutes long, and so I got this shot in between. And then this next one, I was just so excited. I was looking at the images in the car right after as we were heading out. And then here we are in Paris,
Arkansas.
not the actual Paris.
They had a little Eiffel Towers.
They
there,
did. It was very cute. And so we saw these chalk drawings that everybody
Yeah, it was
who was there visiting wrote down. It was a lot of fun. And then here we are, starting our journey, April 6th, where we got together at 7:35 in the morning
Several
to start our
people
trip.
from Griffith Observatory. So,
Now, is that Ian with you there? He's the one
so-
that does our beautiful
Art-
our
yeah.
artwork
Yeah.
for All Space Considered, those of you that have seen that online and elsewhere.
Shout out to Ian.
Shout out to Ian. Great
Yeah.
job on those.
So lots of fun.
Yeah.
Yep.
Yeah.
Well, congratulations on being in that art show and the wonderful piece, though, Ginger.
Thank
It's
you.
really
Thank you very
terrific.
much. Yeah.
Yeah.
And the next solar eclipse will be the next solar eclipse is next year in Spain. So still an accessible location and a sunset.
It's short, though. It's
location.
like a little. It's under 2 minutes.
Yeah, it's under 2
And,
minutes.
I'm thinking about maybe going to Iceland. It'll be cloudy there, but at least I'll get to go to Iceland.
I would not go to.
So-
I mean, no, I personally would not. I'm going to go to Spain, but I highly recommend people.
I'm preparing for Australia in 2020.
Yeah.
Yeah.
So,
Well, I'm also thinking Egypt. And
Egypt 2027. Start booking it if you want to
27,
go.
right.
It's going to be
Yeah,
pretty
everyone's going
packed.
to that one.
Yeah, everyone's going to that.
Well,
Yeah.
folks, we had a huge event happen across the entire nation. The Aurora Borealis was visible in literally every state if you were somewhere dark enough. I like to point out that Nevada, why is that? That's kind of a lame picture of Nevada. That's where I grew up. Hi, Dad. Hi, Mom. Well, it was cloudy across much of Nevada. Even California had a lot of clouds. Oregon did too. That's why you're seeing it through the clouds. But literally, these are pictures taken from all the different states, and these are of the aurora. And as proof, here's a shot from Joshua Tree that was taken, that was done by Ed there. Beautiful picture. I saw that on Facebook and asked if we could use it. Just wonderful stuff. Ginger, you found this one.
Yeah.
Where-
Had to do that. Yeah, South Dakota, I think.
I think it's in South
So.
Dakota. And this is all on November 11th. It was the 11th and 12th that these hit.
This one looks like a face.
And this is an interaction happening with our atmosphere and our magnetic field, and you get these colors, and the colors are dependent on the chemicals that are up there. So you're seeing the glowing gases, and it depends on the layers. You can get these beautiful pillars, and they move around and dance if you can actually see them with the naked eye. They'll shoot left and right. It's a very active
To stay with
look.
the chocolate cake, I tend to describe it as a layer cake.
Oh, yes.
The aurora are, a layer cake where you get this green usually at lower latitudes. You will never get green down here unless it's
No.
the apocalypse.
Well, was this a
but-
record-setting event, Laura May?
So, yeah, this is the interesting thing is that I think many people, it's great because now people are so excited about it that every time this happens, people think, this was the storm of the century. But it wasn't even the storm of the century. So this is a shot I took last year from Mount Wilson, or just outside Mount Wilson Observatory, and that was a more powerful storm.
Yeah.
So this was a G5, and we could see those pillars very clearly. Not necessarily the case this time. So, you will hear all sorts of claims about how strong a storm is. And it's also, keep in mind, we have a lot of social media now. People are broadcasting all these images, which is pretty amazing. So this was a citizen science report. You can, in fact, contribute to this research if you saw them this time, or even if you photographed them. There is research being led by Hisashi Hayakawa at Nagoya University in Japan. So he collected reports from various people and collected all of this and mapped it out, and you can see how far south this was visible. That's pretty incredible.
Yeah.
I want to say Nagoya might be a sister city of LA. I'm looking up at our deputy
is it?
director. He's not sure. I know we have some in Japan, and
Yeah.
Nagoya is in the back of my mind, but I could be wrong on that. So
We will, by the way, link, so if you saw them, if you're watching us online, we will send the link so that you can file a report on them online, or go to our YouTube if you are here and you saw them. But this is not the farthest south that they've ever been seen, right? Again, we have data from quite a long time ago. And this was a very, very famous storm in 1872, the Chapman-Silverman storm. And auroras were visible as far south as Bombay and Khartoum in
Wow.
Africa, right? So you can see all those little dots, again, so close to the equator. It's pretty remarkable. Very fewer sightings of the southern lights. So keep in mind, when we get the northern lights, we also get the southern lights. But those tend to be more concentrated over Antarctica. So people in Australia and New Zealand will see them, but not so much down here. So even though we don't have pictures from 1872, we do have amazing art, right? For many, many centuries, people actually made art of the aurora. I'm sure perhaps there's some petroglyphs out there maybe that depict them. And this was such an image that is from Okazaki in Japan. And so you can see the artist, actually, it's pretty remarkable. They drew these kind of pillars, and that is a recurring theme that we see in old art about auroras. They see these pillars very clearly. Keep in mind, they had a little bit less light pollution.
Yeah. Now this, of course, is from the recent event on November 11th. This was from Minnesota, but folks are engaging with it in a similar way as that artwork. So let me get a photo of my dog with the aurora. Just like let me do a painting with, perhaps that was his wife and daughters in that, or who knows who was in the picture, the painted picture there by the artist. But you also get features like this with really strong aurorae when you're getting up underneath where they're coming from. So you're almost peering up through the magnetic fields rather than seeing the pillars. You can get these sort of, I don't know, they're beautiful. I've never seen it like this. But
I have, but only at very, very northern latitudes.
Yeah, northern
latitudes.
latitudes.
It's pretty remarkable. To see this down in Michigan is incredible.
Yeah, it's in Michigan I saw them as pillars, but you're supposed to be in maybe Iceland or much further
Alaska,
north to see this. Alaska,
Canada. Yep.
Yeah. Now, also, this is just an amazing picture. Again, Ginger, you found this. This is the Clark Bridge over the Mississippi River. So literally, bright lights on a bridge, and you're still able to see the aurorae. Cameras only have so much dynamic range. You can't capture bright things and faint things at the same time generally. So the fact we're seeing these aurorae and the bright bridge lights at the same time, and the city lights behind, this is kind of crazy.
Yeah.
It's remarkable. And seeing the greens and reds in that layer cake.
So many greens.
It's really neat. But this is the sort of thing that had people prompting a lot of messaging about it.
I started receiving messages, in fact, from Texas, from southern Texas, about 2 hours. It was about 8 p.m. in Texas, and then I got messages from Colorado, and then I got messages from Philadelphia, and then I got messages from Canada, and then here, and it's pretty remarkable. Just again, more people are much more clued in on it, and they understand now, that these things are happening, and that this might keep happening, and they're looking out for them, which is great. And again, there is a lot of community. It's just like the eclipses. So, join some groups online, download an Aurora app, and make this, if this is something you really want to see, there are ways for you to be informed on this. And of course, NOAA and the National Weather Service, they put out alerts. So there was an alert that was put out about a day prior. We tend to know we'll talk a little more about what causes it, but we do get alerts a little bit ahead of time, sometimes a day or so, sometimes 2-3 days, depending on the event. So NOAA did indeed put out a G4. The scale goes up to 5, so this was going to be a strong storm. And of course, we can predict these because they come from, no, not Griffith Observatory, but they do come from our friend the sun, right? So all of these little dark regions you are seeing, all of those are active regions that contain sunspots. And you can see there is that particularly enormous one right up there. I think it was active region 4274, I want to say. And those regions will occasionally emit these massive flares, right? Huge amount of energy that come out of these. They are eruptions of ultraviolet light, and you can see these regions kind of lighting up. Now, those regions will rotate also. So they take some time, they rotate. You're seeing a time lapse. Usually it's about 20 days. So that's a full time lapse, and we can see the changes in that region. And the changes are in response to all of the shifting magnetic fields that are inside of the sun. That's why you're seeing that region completely shifting. This is an up-close image. And it was actually starting to flare on this image. This image was shot actually by someone I know, not from a professional observatory, believe it or not. You can actually get equipment and take these kinds of remarkable images close up of the sun's surface and texture. And here is part of what caused the storm. So what you're seeing here in the middle, blocked out, that is our sun. It's just a filter, so that's why it appears blue. And those little ejections you're seeing, almost looks like spurts of gas, and including this one, massive, massive coronal mass ejections. So very large amounts of material that come from the sun. And you notice all these little flecks that come on at the very, let's play this again, at the very end, and that is indicative of a huge, very, very powerful coronal mass ejection. It overwhelms the detectors with radiation, and that is why you are seeing this. And so think about it, those ejections, it's a bunch of magnetized material from the sun, and it forms a kind of rope. And that rope interacts with our magnetic field. And this is what happened. There are modelizations, and you can really see why we call it a storm. Our magnetic field that is protecting us, generated, of course, by Earth's core, and then you see those interactions with those waves, those kind of ropes of plasma that come from the sun. And now this is a visualization of our magnetic field as it normally is, and then when it gets disturbed by, again, all of that energy, that interaction between the coronal mass ejections and, of course, our magnetic field. Now this is what we call the auroral oval. So this is the region where you traditionally see the auroras. You can see it is centered, as we were mentioning earlier, Alaska, Iceland, Greenland, Canada. And you can also tell the time of year a little bit. Again, you've got this kind of, the poles are seeing light, but it is usually, again, constrained. That probability of seeing them is pretty high up, northern latitudes. And this is what it looked like last week. So you can really see how extended that auroral oval is, how high the likelihood of seeing northern lights becomes. And this is a rather remarkable image that came out that shows it is a composite image. So we've added up a lot of images over a 30-hour period, and you are seeing that auroral oval. So this was caught by a radiometer that's on board 2 satellites, so NOAA 20 and NOAA 21. And what it does is it detects electromagnetic radiation, both in visible light and also in infrared light. And so it was able to get this extraordinary image, I know it's black and white, but of this day and night band collected together. Here it is centered over the United States, so really remarkable to be able to see. And again, when it gets very high up, we see it further south. It's another proof that the Earth is round, since apparently that's been debated recently.
Oh, don't bring that up.
That's right.
We don't have time for that. We need to move on.
And in fact, whilst this is interesting to us and we love seeing it, and it is, of course, sometimes a concern for some satellite companies, there are people up there, right? Not just satellites, there are astronauts up there. In fact, I think right now there's about 9 people up there. Does that sound about right?
7 on ISS and 3 on
That's right,
Tiangong.
yep. So there are 3 Chinese cosmonauts, there are, I think, 4 Russians and 3 Americans.
So what did they see, though? That's the question.
Well, so first they received instructions. The different astronauts had different instructions on, some of them did have to go in specific parts of the ISS because this is a large amount of radiation and they're a little farther outside of our magnetic field. But this lady on the right, Zena Cardman, was able to get this remarkable film. I had never seen actually a geomagnetic storm shot by one of them. And you can really see it's a storm because of how elevated, you see that red light on top. That is our ionosphere that is being expanded. That is part of why it causes problems for satellites. It's the upper atmosphere gets a little puffier and we get a lot of drag on those satellites. But really remarkable image footage that she was able to capture. And this was, I wanted to show one specifically from a dark sky. I'm a little biased because I just worked there, but this was shot at the Grand Canyon by their dark sky project manager, Matthew Young. And you can really see that curve you're seeing. that is kind of the edge of that auroral oval that you are seeing from much farther down. And the fact that you're seeing green as far south as Arizona, the Grand Canyon, again, really remarkable. This is one of the advantages of dark skies and of fighting light pollution. We could see the auroras over Griffith Observatory, for example, if we didn't have light pollution in Los Angeles. We'll keep fighting for this. I believe in us one day. But being able
I would say don't hold your breath for LA being like the Grand Canyon, but it could get better,
could happen.
folks.
We will fight for this. I was chasing from Los Angeles, and I was chasing from my home, as I usually do, and mostly using webcams in various locations. So you can do this. You can load various webcams. This was the webcam at Mount Wilson Observatory, and we were exchanging this image with multiple people and trying to understand if that little kind of slightly pinkish tint you're seeing there was reflection from sunset or something. And then eventually I realized it was a gap in the clouds and that was the aurora right behind it. Of course, the one day that Los Angeles was incredibly cloudy was on the day that we had a geomagnetic storm. But this is an image I got from the Mount Wilson cameras, from the webcams, and so you were able to clearly see them. So you can see them from here. Last year they saw them from San Diego. Again, really remarkable to be able to see this. This was an image shot by someone working there. As an aside, I do want to point out that if you hear about this, perhaps don't go to Mount Wilson Observatory. The grounds are shut, so you will not be able to see something like this. There are very few turnovers. There are better mountains to see them from. They have a good webcam that you can check, but it's worth keeping in mind they are a functioning observatory. And the grounds are closed off. So this was, I think we've got a freeze on. There we go. This is the remarkable image that Anush, who used to work at Griffith Observatory, shot that night. We went up there and saw this remarkable northern lights through the clouds, right?
So hint, this is a joke, everybody.
This is a joke.
She just colored that over there. She saw
I convinced people.
Yeah, she saw nothing.
I'm impressed. And this
there are
was
a lot of fake ones out there, so beware.
And there are, in fact, Ginger and I were exchanging some remarkably fake-looking images that were made in AI. But this is a real image, again, from Joshua Tree, with Jupiter you see on the bottom right, and Castor and Pollux. So, you are able to see these with the naked eye. Your camera will always capture more because the detectors on our cameras are more sensitive, and at night we see in black and white. But there were a couple of reports that might convince you that they're aurora, but they're not. So this was an image that was headline news actually on Space Weather and other websites from El Salvador. The reason it's a little blurry and it's shot in this diagonal was because they were trying to capture the bioluminescence as well. You can see that kind of hint of blue there in the water, but these are not the aurora. So they were shot that same night, and I think they thought it was the aurora, and that certainly was published everywhere, but it's a little too uniform, right? So the aurora is structured because they're caused by Earth's magnetic field, and this is actually air glow on that picture. So you can see there are these various lines, and this is just accumulated sunlight essentially, held by particles that gets released at night. This is very common. You will often see it in images of the night sky, the Milky Way. It can be green, purple, reddish. So it's worth keeping in mind, especially if you report things as having seen aurora, to kind of check around as to what you are seeing. Yeah. There was this incredibly fake image that went around as well that I saw in a lot of groups. And again, not the aurora. You will usually get green and red. Generated. But part of the reason that also it's difficult, a lot of people complain to me, well, why didn't we know? Why wasn't this in the news 2 days prior? There are lots of reasons why it's very, very difficult to predict the aurora. So what you're seeing here, this is a new visualization I discovered recently. This is what's called an ensemble representation. So it's a tool that modelizes different scenario for one same CME. So there are a couple of different ones modelized here, but when you see them going in the same direction, you are seeing one CME, so one of those ejections from the sun, modeled with different scenarios, such as its speed, the drag it's going to encounter, its interactions with the solar wind, right? So the little spheres you're seeing, those are the planets. We've got Mercury, Venus, and the Earth on there. And the squares are satellites like Solar Orbiter, the Parker Solar Probe, because we want to know when these things are going to arrive, when these ejections will arrive towards us. But again, this takes remarkable amounts of modeling. I didn't think the storm was going to be strong enough to see from here, and I've been chasing the lights for 15 years. So this is a really, really difficult science to predict, and we have multiple CMEs. Some of them will cannibalize each other as well. And also there is somewhat of a misconception as to the fact that, oh, it just arrives and it just goes straight to our poles, funnels down, but our entire magnetic field plays a role. So our Earth has this little teardrop shape behind it. It's called the magnetotail, and all of that energy sometimes gets funneled down from those ejections, and then there is an effect like a rubber band snapping back. We call this magnetic reconnection, and that will come back and create substorms within the geomagnetic storms that will sometimes intensify. So that may be what we saw for about 20 minutes down in Los Angeles. It was around 8:30 p.m. We saw one of those substorms, and all of this is part of an enormous structure in the solar system that is called the Parker spiral. And the Parker spiral is a magnetic structure that is dragged along by the sun as it is rotating. We and the planets are embedded in it, and there's a lot of modelization that tries to understand when will we be impacted, how strong will the storm be, because also there's a lot of technology, navigation, aviation that depends on this.
Yeah. The spiral you're seeing, by the way, is like a sprinkler.
Yep.
Those are regions, holes in the corona holes that material can come off the sun and it streams out, but just like a sprinkler, the sun is rotating and the material comes off in those spirals. And the magnetic field that is funneling that material is the Parker spiral. So it's all complicated. It's the magnetic field, it's the plasma from the sun. It's really hard to predict, long story short. We're going to end this section just with a few pretty pictures. If we lost you there with some of the technicalities, we want to go back to some beautiful shots. This was taken from Pennsylvania, just some fields there in Pennsylvania, so fairly far south. This is Yosemite.
Wow.
So beautiful shot in Yosemite Valley there. And then this was taken in Sedona. So all the way down in Sedona, Arizona, and you can see this is Aurora. It has more structure to it, like Laura May was saying, versus the even sky glow. And then finally another shot from Roosevelt Lake in Arizona.
You've seen cacti with Aurora.
Yeah, just strange. And then I'd imagine being on the ski lift, taking a trip at night, riding up the top of the mountain with the Aurora around. It would be just amazing. So we don't know if this will be the strongest storm this solar max. Probably. This was remarkably strong. The strongest one we'll see for the rest of it. Last year's storm was stronger, to be clear. But maybe keep your eyes open, watch spaceweather.com, watch other things.
There's usually about 1 to 3, G5 really strong ones. We've had one, but this is still a fairly weak solar cycle.
It is, yeah. So this is, we'll see. Fingers crossed there's more, because boy, it's a lot of fun.
Yeah.
Well, moving on, who recognizes this star cluster? I do. This is the Pleiades, and we've got a story about the lost siblings of the Seven Sisters. Now, as you can see here, there's more than 7 stars there. This is what's known as an open cluster, and all these stars form together. You're seeing mostly bright, hot, young stars. They're B-type. They don't live very long, actually, so they have to be fairly young. Now, you can see there's the Pleiades up above this telescope. This telescope is the Subaru telescope on the top of Mauna Kea. And does anybody know what Subaru means? It means Pleiades. It's the name for the Pleiades. So this telescope is named after the Pleiades, actually. And the Subaru emblem is indeed the Pleiades, although they only have six of the stars. And somebody said the 7th stars maybe is the car. And I don't know. This is not a Subaru commercial. Yeah, exactly. Not a Subaru commercial.
Everybody go up to 6.
But this result was not a Subaru result. This was combined data from the TESS satellite and the Gaia satellite. So they went in and found stars scattered across the sky. This is an artist rendering, supposed to be from down in a well, looking up at the sky up above. And the Pleiades is in the center. And all those little dots that are there, the white dots, are stars that they went and measured their age using the rotation speed of stars. Stars, as they age, slow down and rotate more slowly, so you can get a rough age estimate by how fast they're rotating. And then they also looked at their positions and how they were drifting, and they were able to figure, could these stars have come back together? Could they have belonged together? And they found about, they have 3,091 stars in the membership catalog, and about 1,600 are above the horizon at any time. So this is a loop, sort of a stream of stars that goes all the way around. So how did this happen? Well, stars like this, clusters form in star-forming regions. And this is in the Large Magellanic Cloud. This is the Tarantula Nebula, or 30 Doradus. And you can see that cluster of stars that's forming from this cloud of gas and dust. Well, eventually the gas and dust gets blown away. Some of the stars will migrate away. They'll kind of flow out of the cluster. And you're left behind with an open cluster like this one. This is actually the Beehive cluster. You can see this through a small telescope in the sky. And little by little, the stars lose, and there's not enough gravity to hold them together forever. It's a little like going on their travels throughout the Milky Way. You run into a giant molecular cloud or get a little too close. The tidal forces strip some stars off the edge of your cluster. So your cluster's evaporating with time. And now, the Pleiades, what's left in the main cluster in the center, the ones we see here, but we know that there are siblings scattered across the whole sky now from the Pleiades, and they've tracked those. So a little bit of galactic archaeology was done, which is always fun. Astronomers also identified a growth spurt in a rogue planet. Now you might wonder, what is a rogue planet? Well, it's a planet that doesn't have a star. It's just out flying around on its own. We always hypothesized these might be possible, and the idea was that they were probably tossed out of their solar system with some sort of interaction, a three-body interaction, two objects interacting, and then you've got the star, and when that happens, you can actually toss one of the objects out. Well, this one's weird because it's gaining mass. It already is about 5 to 10 times the mass of Jupiter. It's something like 620 light years away, so it's a fair distance away. Well, when they looked at it, with the Very Large Telescope, and they measured it with a spectrograph, they found that this thing was glowing in the infrared. It was actually hot. Now, this is an artist's video of what's happening. The only way to make this object hot is to have material that's falling onto it. And they've measured, they saw a growth spurt. A whole bunch of material fell onto it, and it caused it to glow. And they figured out this must have a disk of gas and dust around it that's dumping material onto the planet periodically. If I said star, I was wrong. It's glowing like a star.
But it's accreting mass at the rate that a star
would. Yeah, this is the most mass we've ever seen a planet accrete. So craziness, and what is it doing out there on its own? Was it part of the solar system? Because when it gets thrown out, it shouldn't have held on to this disk of material necessarily. But I don't know. I would want to see some models. I'd want to see some simulations of it. But
it's also very young. I think it's
very
about
young.
1 to 2 million years old.
It's very young, and they were saying that this is probably the disk of material it formed out of. So did this form on its own and never had a star? We're not supposed to be able to make things this small without already having some grains around. So it's kind of, we've seen this before in the past decade or so, planet formation, star formation. It's being mixed up a little bit with evidence like this. So it's a fun time for people that want to build planets, because maybe there's other ways to do it, other ways to put it together. Tonight we have a mostest for you. Yay. And our mostest is the hurricane, Hurricane Melissa. Now, indeed, this was tragic for some folks. This is serious, the storms that are hitting, but it's also fascinating dynamics, fascinating weather that's happening. And we have technology to be able to watch these and warn people. And it's very important that we support our satellites and support this sort of research such that we can learn about them. Now, one of the things they did was drop things like this. This is a little probe that got dropped into Melissa, and they let go of it, it flies in, and it measures wind speeds. And when they measured the wind speeds, they picked up a speed of 252 miles an hour. Which made the folks making the measurements be like, are these numbers correct? Is this data any good? Because that was the highest wind speed ever measured within a hurricane, 252 miles an hour. So NOAA looped us in when they saw the high wind and said, that was NOAA asking, are those good? And they answered, yeah, that's a real number. It's accurate. We've calibrated it. This is footage from within. This is a plane that was flying in, and we're going to break into the eye right there. So now we're inside that eye wall. You were going to say something about that.
This is what we call the stadium effect. So this is a classic formation of hurricanes, and that is pretty standard. But what you're seeing, it looks like little baby clouds. I forget how many feet tall this is, but this is ridiculously tall, high up in the atmosphere. So pretty remarkable that they were able to get this footage. I don't think I'd want to be flying through this.
No, one flight turned back. The turbulence were so bad. It was the first time that one of these aircraft that flies into these hurricanes, they were like, enough. no, the turbulence are going to tear this plane apart if we don't fly back. So we're entering new territory with these hurricanes, and I'm not sure what I think about the Mostas being a hurricane, but it was this month.
But it's, you know, wonderful science that we're able to get all these measurements now and refine models, and also their paths, know exactly where they're going and alert people.
People can be alerted. This is important work to be done, and it is tied to climate change. While we can't peg any single storm and say this storm was strong because of climate change, we are seeing stronger storms in general, more stronger storms, and everything is just shifted to more of them. And that's a fact. We're just seeing it. So anyway, well, now it is a little time for some Out to Launch with Jared.
Yeah.
Yeah, what do you have for us tonight, Jared?
I did want to say that the first launch we're going to talk about is the New Glenn 2 launch of Escapade, a mission to Mars. And we were talking about space weather a little earlier with the Aurora, and they actually had to delay the launch because of the solar storm that was occurring at that time, because you don't want to launch your spacecraft into a solar storm and then fry them. In case you didn't know, back in 2023, SpaceX decided to go ahead and do a Starlink launch, even though there was a solar storm happening at that time, and all 23 of the satellites basically were fried on orbit after deployment, and they all failed immediately. So it is very important when you're doing that, especially for something like this, where Blue Origin is sort of getting themselves up to pace and up to cadence. This is a very big rocket, New Glenn. It's 321 feet tall, putting out over 3 million pounds of thrust. And this was its second launch, its first one with a customer payload, which was NASA's Escapade mission. A big rocket with roughly about 1.5 tons of payload on it.
Wow.
So Escapade is taking a very interesting trajectory where it's going to be in orbit around the Earth and then go far out and then come back and head on its way to Mars. So the window for Mars actually isn't open, but they're using a trajectory that is allowing us to open up these different windows so you can essentially launch at any time you want to. So very exciting.
Is it going to stay in orbit around Mars? Is that the...
Yes. So the Escapade spacecraft are going to go to Mars. They're going to study the magnetic field and interactions with the atmosphere, and they're both going to go into different orbits to take simultaneous measurements in different areas at the same time, so that way they can compare and contrast and get a better idea of that. We're getting really good footage out of Blue Origin. I love this this nice slow motion engineering camera footage of those 7 BE4 engines there.
Is there, I saw this the other day on a video, is there water shooting at the pad? Okay, is that to diminish some of the exhaust? And
Yes.
Well,
So-
it's also sound.
Yes, it is. It's for
Sound
essentially
dampening.
acoustical dampening. Rockets are very loud. The exhaust from a rocket can get up to 210 decibels in sound when you measure it on decibels, which is enough for a rocket to literally
deafen you?
literally vibrate itself apart.
Wow.
So we use water to actually dampen the noise with that. You'll recall that the first Starship test flight that SpaceX did, they said they didn't need a bad water system. And we all know how that
a lot of
ended.
concrete went flying.
Concrete actually cleared the tower before the rocket did. It's the first time the pad's ever gotten above the rocket before it left. But
We love the
you know,
hubris.
live and learn, right? So the new pad they're building for their Starship rocket is going to have a new water system integrated into it, not the sort of Band-Aid patch that they have at the moment. That still works. But this was really great to see this in action, and then just this beautiful tracking camera action shot of this rocket. And it's kind of hard to comprehend the fact that this is almost a football field long.
Wow.
Here, and we're watching a football field fuel tank with these two little spacecraft.
Is it as long as the Saturn V?
Just about 50 feet short, roughly, of Saturn V. So
Yes, it was an incredibly clear day.
Yes.
Because they were able to track this with cameras from the launch site all the way through separation and second stage lighting, and it was a. Go watch all the footage, folks, if you haven't.
Yeah.
I recommend checking it out.
And Blue Origin's also been posting footage as well. There was this really great footage that we had here looking up from the booster for stage separation. So if you ever wondered what that looks like, here you go. You see a little pusher system push on the upper stage, and there go the two engines, and then we'll watch the engines light as well here. And they go. So very nice. So, and they're using hydrolocks on their upper stage, so they're actually burning liquid hydrogen, liquid oxygen together, which is very clean burning. And then this was the big thing, which is that they're also making New Glenn reusable. So this was the second time they were attempting to land the booster, and you could see that booster's coming in nice and smooth. It's almost hovering down to their landing barge that they have, and here it is landing on the deck of the barge, Jacqueline, and a very cool little detail that we'll see here. So first of all, I could not believe it landed.
I was surprised.
The first flight, the engines actually didn't relight for the entry burn, so they had no attempt at all. But this one, everything worked perfectly. And then this little cool detail, look at the feet on the landing legs here. You'll see something in just a second, which we're all wondering, how's it going to get attached to the landing barge here? Boom, that little thing, that was a welding system built into the feet on the landing legs. Wow. So it just welded itself right onto the barge. So that was really cool to see that happen.
Yeah.
But Blue Origin, welcome to the show. We now have the second rocket, orbital class rocket, that is capable of reusability. Really important reusability because it brings your costs down. You can imagine if we were flying aircraft, say I was going to take a flight to Paris, and when we got to Paris, we just threw the plane away. It would kind of keep things expensive, right? So that's what happens with expendable rockets. You're throwing the plane away but to reach your destination. With the reusable rocket, we're refueling it, we're putting stuff back on it and flying it again. This is critical to making things cost effective and important to the future of spaceflight, and making sure that it's not just something that's done by people who have or have not the money, but also that everybody can come along on this. This great adventure that we're going to have throughout the solar system. So very excited. We now have a second provider that's going to put pressure on SpaceX, and we'll see how SpaceX responds to this. So,
well, they've been landing stuff for a while. How many have they had?
they sure have. In fact, it's funny you should mention that, Doc. We got this launch, which happened last week out at Vandenberg, so a local launch. And there you go. There's your
the
sound
water
suppression system right there. And I encourage anybody here on the West Coast to go down to Vandenberg, because you can actually stand on a road called Ocean Avenue and look at them as close as you can out in Florida, sometimes even closer. And you can really feel it. But this Falcon 9 did what Falcon 9s do, which is the booster came back to landing zone 4 and landed. And you're probably thinking, well, that's not really a big deal. Falcon 9s do this all the time. Well, the big deal here is that this is the 500th booster landing for a Falcon 9.
500.
So we had New Glenn with their first, and now SpaceX with their 500th. And that's, I suppose, what you get with a decade lead.
I always feel like I need to speak up about this. NASA was doing this sort of stuff back for Apollo. We had to land a rocket on the moon. It was rocket powered that landed. It had people on board.
Absolutely.
So NASA sort of led the way with this reusable technology. We didn't do it with the boosters, so credit to the folks that did. But this is all built upon knowledge. That's how science works, is you have the scientific body, you build on that, then you do more engineering, you make it better, and you share with folks through research papers.
Presumably Blue Origin learnt from also SpaceX's.
Yes. Yeah. Turns out there are a lot of engineers that work at SpaceX that ended up getting hired.
I was just going to say, that's how...
So that's how it goes.
Yeah,
also,
you become a valuable engineer, and people will pay for that.
Exactly. And as someone who works in aerospace, everybody's kind of running back and forth between each other. Obviously, you don't take what you learned at the other company with you. That's what NDAs are for. But you do sort of take this sort of tribal knowledge with you to other different places and use it to everyone's benefit. And SpaceX really benefited from McDonnell Douglas's work in the 90s on a program called DCX, which was doing vertical takeoff, vertical landing before Falcon 9 was doing
that cone-shaped thing?
It was the cone-shaped one. It's my favorite, what could have been, what could have been will always be better than what is. And DCX is like my absolute favorite thing. Cool. And it's my favorite thing to bring up when everybody's like, SpaceX did it first. And I'm like, you're about 20 years too late. So, yeah, pretty cool there. But this was to deploy the Sentinel-6B mission, which is a ocean-level monitoring satellite. So, 6A was actually deployed 5 years ago from the same launch site. So very, very cool.
Yeah. That one shot of the Hurricane Melissa was a Sentinel shot from an earlier mission.
Yeah, so it's doing a lot of great work for us on orbit. Now, this is actually from Japan, from the Japanese Aerospace Exploration Agency. They have a new cargo vehicle that's going to the International Space Station called HTVX, and we're very, very excited that they did that. They basically developed a whole new rocket, the HTV3, that allows them to do that, and it successfully made its way to the International Space Station and delivered a couple 100 kilograms of cargo. It's going to be able to deliver up to about 4 tons of cargo at any given time, and also dispose of trash and other things as well. But we're very, very excited about it, so can't wait to see more of that happen. And then I do want to talk a little bit about China too, because they had a bit of a issue, I guess is the way to put it, with their Shenzhou spacecraft up on their Tiangong space station. Shenzhou 20 took damage from space debris while on orbit. And China is usually very secretive about anything involving their space program, but they publicly announced that the Shenzhou 20 crew was not going to be able to come back in their spacecraft because of how much damage it had received from the space debris strike. So the Shenzhou 20 crew went into the Shenzhou 21 spacecraft, and they returned safely last week, so we're very glad that all 3 of them were able to return, and they're going to send up an empty Shenzhou spacecraft so that the current crew that's on board that came up in 21 can come back in their own spacecraft.
21? Wow, they've been up there for a while.
Yeah, Tiangong has been crewed, I want to say, since 2020.
Like that,
continuous human presence on board.
Do they have a way to get off it now if something were to happen?
Yeah, they're working on it.
They're working on it. Okay.
So yeah, so from what I understand, it's sort of a similar situation where a couple years ago we had a Soyuz, for whatever reason, sprung a coolant leak, and they were unable to use that Soyuz, but it was one of those things where in a pinch, if they really needed to, the astronauts could get in the Soyuz and kind of hang out in it for a couple days and wait for rescue that way. So similar situation, but from what I understand, China is moving full speed ahead as fast as they dare to get the new Shenzhou spacecraft up
Is
there
the reason that they released this information in any way related to international cooperation on getting rid of space debris?
So we think it's 2 reasons. So 1, the space debris, as I make more space debris on the ground here. But 2, also, just in case rescue did actually need to happen, there is treaties and other things that multiple spacefaring countries have signed that say that we're willing to step in and help out in the event of a significant emergency at any point in time. U.S. is a signatory of that. China is a signatory of that. Russia is a signatory of that. Europe as a whole, through the European Space Agency, is a signatory of that. Canada, other countries, Japan. So basically, a lot of us think that they announced it just in case somebody needed to come forward and help them out a little bit. So. And then Artemis 2 is getting stacked as well, so we're looking forward to that.
Shutdown's over?
Shutdown's over.
Sure hope so.
And this video, we're not going to watch the whole thing because we need to move on. We're running a little behind here.
But sometime in February, that is the opening window for humans returning to the moon for the first time since 1972.
No, they're not going to land on it.
Let's go, baby.
They're going to fly around it this time.
Yeah, they're going to fly around. You can do a free return trajectory, but I don't care. It's a spacecraft going to the moon with humans on board. I'm excited.
Yep.
So.
Yeah, it's very cool. Well, Ginger, we have a few beautiful pictures to show from astrophotography, and this is a lovely shot of, what is this place?
Coming back down to Earth. Where are we?
We're back on Earth here at Griffith Observatory. It's a beautiful shot by
our very own David Pinsky
here.
Thank
David,
you so
wonderful
much.
work. He's here in the audience with us, folks. So thank you, David.
All right, this one I'm super excited. This was released yesterday by James Webb, and it's to show the first 4 dust shells around 8BEP. Which is a ray Wolf-Rayet star. And so the previous images of this, there was only 1 dust trail, but this one shows 4. So pretty exciting.
Very
it's just
windy
gorgeous.
stars.
Anyway.
And then we have this beautiful image, Sagittarius B2. This is the near-infrared camera, and then we also have the mid-infrared. So you can kind of see the similarities and just the difference in the color there as well. And this one, another pretty picture. This is the Red Spider Nebula, also caught by the James Webb. So last month, if you saw last month, I did a spooky images for Halloween, and the Spider Nebula was there, but this is our newest image of it for October.
Now, what causes this? This is a star in the center.
Yes.
And this is the atmosphere of the star being blown off as it dies. Now, likely it has a companion in there to get these sort of hourglass figures. Usually there's a companion stirring things up a little bit. Yeah.
And then we have Caroline's cluster, Caldwell 58, which is an open cluster. And I chose this one just because it's a great target for amateur astrophotographers. Astrophotograpers, if you have binoculars, you can check this one out. It's a great winter target.
Well, and Caroline is Caroline Herschel,
Caroline
which
Herschel,
is the sister of William Herschel, who's on our astronomers monument.
Yeah.
And she should be recognized as well. She was a very good astronomer in her own right. Took a lot of the data that he used to make his discoveries as well. So it's good that we recognize her.
Yeah.
Discovered many comets.
And then we have another David Pinsky image. This is of the moon on October 30th with a Lunt 80mm refractor and Canon camera. So great shot there. And then, of course, I had to include the Pleiades because we were just talking about the Pleiades. So this is Pleiades M45, also a great winter astrophotography target. I captured this with just my Canon 5D camera, and it's a lot of fun.
How long of an exposure to?
I think I got only an hour on this one, so.
Only an hour, Ginger.
Yeah, I mean, I try to go for, as much as I can, because you get more data, you get more of the light and the stars, So, and then I also got this one. So this one, is it a satellite, airplane, or is it a comet? All right.
It's in the satellite trash pile.
Yeah.
If you look just right where that horizon line is, you can see Comet Lemmon. This was taken at the Grand Canyon, actually, while I was visiting Laura May during your residency there. So it was a lot of fun.
Pretty, given the, there's such good skies there, and it's kind of sad to see all of those satellite trails.
It's going to get worse anyway.
All right, and then we...
Well, everybody's launching constellations. It's a thing.
This is from one of our telescope demonstrators, Anthony Perkic, and this was the Aurora sighting on November 11th in Landers, California. So pretty neat. We actually see a little bit of color there.
Nice job, Anthony.
Yeah, thank you.
Great shot.
And then our other telescope demonstrator, this one is another Anthony Perkic, Comet Lemmon. This was Leo Carrillo State Beach.
Wow.
So
Leo Carrillo, that's not
even
far.
with light
not
pollution,
even in a dark sky.
Yeah.
Remarkable.
And then another one, this is from Todd. Thank you, Todd. So that's a pretty great shot of Comet.
Do you know where he shot this from? Looks like Joshua Tree.
I'm not too sure. I think Joshua Tree,
Wow, really remarkable.
And that's it,
And that's it. So, folks, now it is time to have our guest join us. So, Bryce, why don't you come on up? And Laura May, why don't you take the lead seat here? Because Laura May is actually on a bunch of the research with Bryce. You've been on observing runs, so...
Well, Bryce will present his work, I think, primarily first.
Well,
I guess we don't need to switch.
We don't need. We can stay here, but I'm going to let you lead the interviewing of him. I'll still ask some questions, of course. But first, Bryce, you're going to present some information for us, and we need to hit.
I think it's that one right there. Stage laptop.
Yep. Stage laptop to LIH. There we go. And then.
That's your background?
Do y'all like my wizard?
Yes.
It's a comet wizard.
So Bryce is an astronomer that works for Eureka Scientific and is an expert in studying asteroids and comets and interstellar objects that come and visit us. So we are very lucky to have Bryce Bolin with us. So everybody, let's welcome Bryce Bolin to All Space Considered. Thank you so much for joining us. So Bryce, take it away. You're going to give us a little intro to what you do and what this is all about, and then we'll have some time to ask some questions and chat with Bryce. So take it away, Bryce.
Sure. Can y'all hear me okay? Yeah. Oh, great. Fantastic. Well, I'm glad to be here. So I'm going to talk about some interesting topics that have been in the news recently. We've had this interstellar object 3A Atlas in the news, and I'm going to talk about some of the science behind it, as well as maybe some other exotic objects if we have time. But first things first, are there any nerds in the room?
Yes.
Yeah. So there's actually been interstellar objects. Has been a topic in some pop science fiction. So has anyone here read the book Rendezvous with Rama? It's Arthur C. Clarke. So it's actually about kind of similar to what we're experiencing now, where an interstellar object was detected from ground-based surveys, and spacecraft and crew was sent out to investigate it. and it turned out to be an alien spaceship. And there's a movie coming out, 2027. Denis Villeneuve is remaking this, which I think is probably inspired. Hollywood has taken note of these recent interstellar object discoveries, and it's been a hot topic, and so they're following suit with a remake. So I just want to say at the start, when the very first interstellar object was discovered, when Oumuamua, more than 7-8 years ago, this was kind of a running joke among the astronomers, like, oh yeah, it's rendezvous with Rama. And now, so do we have people who are into science fiction Japanese role-playing games? Well, if you've played Final Fantasy VII, do we have any nerds here? Any nerds here? Nerds represent?
Yeah.
There is actually an interstellar object in it. The main villain, Sephiroth, summons an interstellar object to basically destroy the solar system. And he sends this thing. It destroys Jupiter and the sun, and it just causes complete devastation. So that was an interstellar object. Now I'm going to talk a little bit about some of the the parameters which we use to describe objects in orbit around the sun or objects passing by the sun on trajectories. And I was always told a picture says 1,000 words, but a movie says 24,000 words per second. So I have a little movie that shows this, what we call the orbital elements. So orbits are described by three parameters. The first is called the semi-major axis, which is basically how wide the orbit is. If the orbit is described by an ellipse, the width of the ellipse is called the semi-major axis. The eccentricity is how elongated the ellipse is, how egg-like it is like. And the inclination is the angle that it makes with respect to the ecliptic. And so that's relevant for the topic of interstellar objects. Do we have the next screen showing here? Because for objects that have an eccentricity of 0, they're more or less circular, completely circular. However, as you increase eccentricity more and more, they become more egg-like. And when the eccentricity equals a value of 1, it forms a parabola. And for our values greater than 1, it forms a hyperbola. And for objects which have an eccentricity greater than 1, we call those not gravitationally bound to the body with which this orbit is ascribing as to being orbiting around or respect to the primary mass at one of the foci. And for interstellar objects, for the first two, before 2025, only 2 were known, 1I Oumuamua and 2I Borisov. And these had eccentricities greater than 1. Oumuamua had an eccentricity of 1.2. 2I Borisov had an eccentricity of 3.35.
Wow.
And so we have 2 images of these objects. On the top panel here on the right is a Hubble image of Oumuamua, which looked like it was basically a point source. It didn't have a tail, didn't have a coma or anything like that in these images. Where in the bottom panel on the right is 2I Borisov, also imaged by Hubble, which has kind of a fan kind of shaped coma tail extending outwards going into the upper right of the image. And the other thing that's remarkable about these is that these objects had a V infinity of 26 to 32 kilometers a second. So what a V infinity is the velocity that an object has when it is at an infinite distance from the sun, basically where the gravitational interaction and between the object and the sun is basically negligible. So you can think of this as the inherent velocity that the object has before encountering the sun. And so this is very high. For objects that are bound to the sun, gravitationally bound to the sun, they have a V infinity of 0 kilometers a second. So both of these objects had V infinities well beyond 0, which suggested, with strongly evidence, that they originated from outside the solar system. And we have a new sheriff in town, 3I Atlas, so I'm going to talk about the new one that was discovered. So on the left-hand panel here, we have the discovery images of 3I Atlas. It's this little tiny speck in this red circle here, and it was discovered by the Atlas project located in Chile on July 1st, 2025. And on the right-hand panel here, we have the discoverer of 3I Atlas, Larry Deneu, who is a senior software engineer at the University of Hawaii. And so this guy, not only has he discovered 3A Atlas, he's discovered multiple impacting asteroids, mini-moons, other really fantastic objects. And the way he did it is he basically wrote all the software that goes into the images, that analyzes the images taken by these surveys, such as Atlas, to find asteroids and comets, such as 3A Atlas. And he, also a little trivia here is he was at one point my landlord. I rented an apartment for him when I was we used to work together. I've known Larry for more than 10 years now.
Did he work on Pan-STARRS?
Yes, so
Okay.
he was also the chief engineer for the asteroid finding system on Pan-STARRS,
Yeah.
as well as NEOWISE. So he's very accomplished. He's probably the world's best at writing software to find asteroids and
Now,
comets.
does he like
and
to
images.
remind people about how many he's found?
No. He's
humble about it,
no.
'cause
He's
I
very.
don't know if I would be.
He's very. He's very unassuming.
And he should be in the news much more than
he should
another
be.
person. who
Well,
Yeah.
he
talks about
he
this
does
subject.
get in the news. He gets inquiries, and he's very communicable. He's very interactive. He'd be a great person to talk to. His son lives here in LA, by the way.
Oh.
So
if we invited him to the show, he'd have somewhere to stay.
yeah. Well, if he's ever here in town, he could come and tell you about it.
Yeah.
He'd do a much better job than me talking about how this stuff works. So this third one, 3I Atlas, which was discovered on July of this year, has an eccentricity of 6.14.
Wow.
It's huge, and a V infinity of 58 kilometers a second. So that is screaming fast. And this image is one that we took here at the International Gemini Observatory with Shadow the Scientist. Do you all know Jamaica Marshall? She helped organize this program.
She appeared on our Juneteenth episode.
Yeah, that's fabulous.
And she'll be our guest in April, and we're going to do a Shadow the Scientist in April. So.
Oh, that's awesome. So she co-organized this effort to observe this object, this 3I Atlas, with Gemini at the end of August, and we captured this beautiful image right here. This kind of has this.
So
kind
this
of
is
red
an image
glowish
you
color.
took. When you say we, you literally mean.
So
There's a whole group of people.
it was a
Yeah.
collaboration of NORLab, the National Science Foundation, shout out to the scientists, and as well as people from the University of Hawaii. Auroras, I think, was also in attendance there as well. So we helped design and implement these observations and took them, and Jamaica organized a public Shadow the Scientist session where we watched the telescope crew go through the process of pointing the telescope, focusing it, and taking these images. And it was pretty astounding. And we're going to have another one. I'm going to have a slide at the very end where we're going to be doing it again next week to observe 3A Atlas when it comes out of perihelion. So now another thing to keep in mind is that we do occasionally see comets with eccentricities greater than 1. For example, there was C1980E1 comet Bowl, but it had a close encounter with Jupiter that excited it, increased its eccentricity to just above 1. However, the big difference between comets like Bowl, which originate from the solar system and had an encounter with Jupiter that elevated their eccentricity above 1, and those of the interstellar comets is that the interstellar comets have eccentricities much greater than 1, and they did not encounter any of our giant planets. Also notice that Comet Bowl has a V infinity of only 3.8 kilometers a second, where these other objects are screaming fast, 58 kilometers a second.
Well,
3I is going to, sorry.
Well, no, go ahead.
3I is going to be near Jupiter at some point later, I think either in March? Is it
Right.
March?
I'll show you that in a second.
Well,
So
the question I had, though, about it was, will the comet that encountered Jupiter, will it become an interstellar comet for another star, perhaps?
oh yes, probably on the way to the Klingon homeworld.
Okay.
So just to illustrate that point, this is the trajectory of 1I Oumuamua. It had an inclination of 122.7 degrees. And so it was coming basically almost perpendicular to the plane of the solar system. So it was like the solar system was like a target with the sun at its bullseye. And so it was way above all the plane which all the planets inhabit. So it had no way to encounter a gas giant planet to elevate its eccentricity to its value of 1.2. 2I Borisov bears very similarly. It had an inclination of 44 degrees. So that was well above the plane of the solar system. And it had no way to encounter Neptune or Jupiter or any of the large planets to elevate its eccentricity to its value of well over 1. And for 3i Atlas, it had an eccentricity of 6. But the way that which it was coming from, the direction it was coming from, it did not encounter any of the planets. So it's coming from the right side of this plot. The direction of the arrow is pointing the direction that it's coming from. And you can see Neptune is all the way out here and the top right portion of this plot, where Jupiter is at the left side of the center of the plot, and Saturn is way off to the side. So as it was coming in, it didn't encounter any of these planets. So there was no possibility of it, even though it had an inclination of 175 degrees, which means that it's only 5 degrees, it's retrograde. So when you have an inclination over 90 degrees, you become a retrograde object. And if you're 175 degrees inclination, that means you're 5 degrees, but on the other side above the ecliptic. But even at only 5 degrees above the ecliptic, this trajectory, its path through the solar system, took it nowhere near any of the other planets on its way in. On its way out, yes, it will come by Jupiter, but by then it had already had the eccentricity greater than 6 and the V infinity of 58 kilometers a second. So what are the different properties of the 3 known interstellar objects? Well, they're all very different from each other in some pretty substantial ways. So 1i Oumuamua had an inactive appearance. It was point source-like, did not have a tail or a coma, and it had a 2 magnitude light curve amplitude, would imply that it had a very elongated shape, something that looked kind of like this, something like a needle, something where the short side is 6 times smaller than the long side. And let's skip through that there. Whereas 2i Borisov is clearly cometary, lots of dust. We couldn't really say too much about its size because it was enshrined in dust. 1i Oumuamua was about 250 meters in size, but the comet, like 2i Borisov, was so enshrined in dust we couldn't directly image its nucleus. But we used something called adaptive optics observations from Keck, using an instrument called Osiris, which is the Egyptian god of the underworld, very relevant for the study of interstellar objects. And using the precise resolution enabled by adaptive optics, the high resolution enabled by these special types of cameras, we were able to constrain the diameter of 2i to a diameter of less than 1 kilometer. So it couldn't be any larger than 1 kilometer in size. For 3i Atlas, this is also an active object, but it doesn't. When it was starting out, when we first detected it in July of this year, it didn't really have a tail. It had a coma, had a little bit asymmetry, but it didn't really have the telltale, let's say, for lack of no pun intended, telltale signs of a comet. Now, we also observed it in a number of different wavelengths. We observed it also with Keck using their infrared camera, and we could also see roughly about the same morphology, a little bit asymmetrical coma, but really no tail there. Now, in the images I mentioned earlier that we were doing with Jamaica on Shadow of the Scientist with Gemini, in August of this year, a month or so later, this object started to develop a tail, and where the tail was going in the antisolar direction. So in these images, the sun's direction is in the upper right-hand corner of the plot. So this is a 4-panel plot, kind of like the Brady Bunch. So you have on the top left-hand panel, you have U-band, which is blue light. And on the top right panel there, you have green light, G-band, which is green light. And the bottom left-hand panel, you have R-band, which is red light. And then you have, starting to get towards the infrared, I-band in the bottom right-hand panel there.
That's a good set of filters.
Yeah, thank you. So in all four panels here, you can see that there is a tail pointing in the bottom left direction, which is the opposite direction from the sun, which is in the top right direction in each of these 4 panels individually. So it looks very comet-like, let's say, or is starting to look like a comet. And there could be a variety of different explanations for this, being that the grains were large enough that they were sluggish and blowing backwards in the opposite direction of the sun due to solar radiation pressure. Now, another thing about you have to forgive my exploration and use of all the different colors here. I like making colorful plots, so I apologize because of that. My predilection towards making colorful plots, making this difficult to read. But we have here what are the colors, the measured colors of all the different solar system objects. So the asteroids are these tiny little dots which are colored green, red, and blue. Those represent different asteroid types, where those blue stars are Kuiper Belt objects. Those are inactive comets found beyond the orbit of Neptune. And then those green stars are the colors of the comets from our solar system. So it appears as though, let's look at Oumuamua. Oumuamua is this yellow cross there. The location, the color space of Oumuamua resembles that of other Kuiper Belt objects, which suggests that it has reflective properties like distant solar system objects, inactive objects. Whereas the second one, the 2I Borisov, which is represented by this purple cross right here, is more closer to the ensemble of comets, whereas 3I Atlas, which is represented by that red cross right there, is quite a bit more distant from them, which suggests that it's, at least when these data were taken in July, that the comet had a red color. Now it could be getting bluer, and we'll discuss why, but it could be that we are seeing that it has a red color due to the fact that it hadn't really become active, it hadn't really turned on yet as it was coming in from the interstellar space into the solar system.
Yeah, but one point though is the color is not outside the range of objects we see. It has asteroids to the right and left and below it, so it's not that strangely colored.
That's right. That's right. And we also are taking spectra of this comet, which is a spectrum is basically kind of like a rainbow. You've maybe not realized this in your entire life, but you have seen a spectrum every single time you've looked at the rainbow. It's not a perfect spectrum because a raindrop, the dispersive element being the raindrops, the water vapor drops in the atmosphere, are not perfect dispersive elements as a prism or a grating would be. But essentially the principle is the same, is that you're spreading out the light into all its different components. And so what the spectrum looks like in an astronomical instrument is basically in this bottom panel here. It's basically you're spreading out all the light across a line where the leftmost part of the line corresponds to purple light, violet light, and that's why it's colored purple here, where the right side of this line here corresponds to red light, and that's why it's colored red. And directly in the middle, you have yellow and green light, and just shortward of the green light, you have that kind of aquamarine color. Mm-hmm. And so what the different brightness levels is, so you have the color is determined by the position here, but let's say the intensity, let's say the bloom that you see there, let's say the saturation of the light, the bloom corresponds to the intensity in that wave band. So you can see for the green portion of the spectrum here how it's kind of big and fat. That means the light there is stronger compared to where if you go further out in the red, it's a little bit thinner. So that means the white light there is weaker. And you can also see if you go a little bit all the way on the left side of this plot, you see in the purple, there's a big purple bloom. That means the light there in that little purple section is also very, very strong. So the way scientists look at spectra is they take this information, they take this picture right here where you spread all the light out and you can see a bloom, and you turn it into a plot. You basically quantify the brightness in that section of the spectrum, and you put it as a number on a line. So that's what this top panel here, on the x-axis, you have the wavelength number, where 400 nanometers is like purplish light, 500 nanometers is green light, and 600, 700 nanometers is more red light. And then the y-axis is the intensity, is the amount of light that you're getting in that specific waveband. So going from the left-hand side, you see a spike there where the purple is, and that's cyanogen gas at 388 nanometers. And don't worry, it's not really going to hurt us, it's not poisonous, it's out there in space, but there's no way it can get into our atmosphere and affect us. But just a little bit to the right of that, at around 402 nanometers, you have triatomic carbon, which is kind of that, what I call the Don King haircut right there. You have this kind of little spiky thing here. If you watch boxing in the, what happened?
I think hold on. There we go.
We're back.
Oh, there we go. If you watch boxing in the 90s and 80s, you'll know who Don King is. He's this guy with this very eccentric hairdo. So I call it the Don King signature there. And if you go a little bit to the right of that, you're going to get these other cometary gas features called diatomic carbon, which emits light at 473 nanometers and at 517 nanometers. That's where you get this kind of ramping, kind of double like sawtooth, shark tooth looking thing, and where you get the first shark tooth at 470 nanometers, and you get the second shark tooth at around 517 nanometers. And so this right here was taken by a colleague of mine of Comet Lovejoy in 2016. But we took a similar spectrum of 3i Atlas, and this is what it looks like. And lo and behold, you see a lot of the same kind of cometary gas species emitting at these wavelengths. Cyanogen gas at 388 nanometers, triatomic carbon at 402 meters. The Don King haircut is a little bit more subdued there, but it is there. And then you have the diatomic carbon at 474 and 517 nanometers. And the reason why I mention this, what's important, is that these, going back to the colors of the rainbow, this wavelength area of light where the diatomic carbon is seen is what gives the green color. And recent comet images, this was taken by a famous astrophotographer in Germany named Michael Jaeger, took color images of 3i Atlas, and shows that it has a green color now. It also has an ion tail going in the opposite direction of the sun.
Sure looks like a comet.
Yeah, well, it's so the green color is comes from the diatomic carbon gas.
This was taken yesterday.
That's amazing. That's a great
right.
photo.
Yeah.
And if y'all remember in the news, there was this thing about this famous green comet, January of a couple years ago, where I heard that some staff here, they would get phone calls about this thing every day.
I complained about it endlessly at the time.
So this was a comet that was naked eye visible in January of 2023, and this was an image of it taken by Javier Caldera. I happened to be the one to discover it, but you know that's well in the past. This is a zoom-in picture of it, and it's got a nice green color, wouldn't you say? And it was in Newsweek, on the cover of Newsweek, and Sky and Telescope.
We were getting nonstop.
Laura May painted a picture of it right there. She's a very accomplished artist, and she wanted to immortalize the comet with this
and some of the code also,
painting.
and some of the parameters of it.
That's right. That's right. And there's other comets like 12P Pons Brooks and C2012 K1 also have a green color. So it's very common. So I don't want to go into this topic too much, but there are some people who think that these interstellar comets are alien spaceships, but they seem to have green color similar in appearance similar to comets in our solar system. So which way is it? Are these interstellar objects, are they actually comets, or all the comets that we're seeing in our solar system, which are green, are alien spaceships? Maybe all the comets are alien spaceships. I don't know, but I think they're comets.
Yeah, no. But there is one astronomer, Avi Loeb, that's getting a lot of headlines about this, and folks out there might be thinking, well, he's at Harvard, we should believe him. Let me be clear about this. I don't know of a single other astronomer that is trying to sell books as hard as Avi is trying to sell his, because that's what he's doing. All the other astronomers are embarrassed by his activities that I know. It's irresponsible, the claims he's making, and it's not scientific. There is overwhelming evidence that this thing is looking like a comet. There's also evidence that it's a little different, that Bryce can tell us about some of these differences. But it is just...
And it's a disservice to the public.
It's a disservice to the public.
In terms of,
it is.
You know, we have this interesting object that, as Bryce is explaining, is so interesting, even if it falls within the realm of some other objects that we've seen with some of its parameters. And yeah, it does a disservice to science, and especially the dismissal of all the work of people like Bryce and other people who are working very hard on this object.
Well, and Bryce, you would probably love to find an alien spacecraft come flying into the solar system with your work.
Well, that was
A person would win a Nobel. We all would love this.
Yeah.
Every astronomer I know is looking to find this.
So let me say this. So I want to talk about where I think interstellar comets come from and how they form. But let me say very quickly here is that to Avi's credit, he is a very accomplished astronomer. He is extremely well known in the field of cosmology, and he has done a lot of groundbreaking work on the early evolution of the of the universe. Sorry, and I think in terms of the entire topic of astrophysics, not just comets or so on and so forth, and talking about broadly, I don't as a theoretician, I don't know of anyone who knows about astrophysics as much as he does. So we have to give credit where credit is due. Now, I don't agree with everything he says, especially when it comes to interstellar objects. He has his views, I have mine. But he is a very well-regarded scientist, and
But he is not a planetary scientist.
Well, what he is doing with interstellar objects, he does acknowledge other people's work. He has a blog where he does talk about it, but it's his interpretation that that differs from what a lot of the community has. But this is common in science. We don't all have to agree. And if we all thought the same, there wouldn't be progress in the world. Yes, that means some people are going to be right and some people are going to be wrong. I'm not going to get into that. I'm just going to state what I think my opinion is. But this is a normal thing in science, and so one positive aspect that is coming out of this is he is giving a lot of attention to interstellar objects, which we are benefiting from, and he does work very hard at it. He is one of the hardest working people that I have seen in astronomy in general. Again, I don't agree with everything he says. That's why I'm here to talk about.
And there is some level of media expansion because the papers he does acknowledge also, well, it's most likely a comet. He just states his other opinions, and the media and a bunch of influencers ran with these other theories, and that's kind of the bigger problem of the snowball effect of that.
He's very good at citing and acknowledging work. He's very good at following the literature. It's just that he has his own views, which are divergent from what a lot of the other scientists think, which is fine. It's totally fine. Again, there wouldn't be any progress in the world if we all thought the same. So I'm not going to talk too much about the non-natural hypothesis for the origin of interstellar objects. I'm going to talk about what I think is the correct hypothesis, or what I think represents the observations that we're seeing best where interstellar objects come from. And that is they are formed in disks around stars called protoplanetary disks. This is one that we've seen around a star called HL Tau, which was imaged by ALMA, which has a collection of dust and gas orbiting it that we think was similar in appearance and content to our star. Our star had a similar dusty and gaseous disk in its early stage, within its first few million years of its lifetime, within the first few years of its birth. And on the right-hand panel here, we have kind of a zoom in of the kinds of physics that we think are occurring in these protoplanetary disks, which results in the formation of planetesimals. And this is called the streaming instability simulation, where you have the clumping of dust and gas that is occurring in this disk that causes the collapse of these clouds of dust and gas into solid planetesimals on a very short, abrupt time scale within a few hundred years or less, going from dust-sized particles, things that are the size of a grain of sand, into particles that are 50 to 100 kilometers in size. And I'm not going to go through all the minutiae of that, but basically what it suggests is that the formation of planetesimals in protoplanetary disks around stars is pretty common. And so we think this process occurred in our solar system, and that it resulted in the formation of a disk of planetesimals, about 20 Earth masses in total mass, at its outer edge when the solar system was in a more compact configuration where all the planets were contained within 25 astronomical units of the sun. And beyond that, you had this 20 Earth mass trans-Neptunian, we call it the trans-Neptunian disk, consisting of about 1 trillion objects. Now, what happened was the interaction between the gravity of this disk and that of the planets caused the orbits of the planets to migrate. Let's see if this movie will play. Oops, I don't, oh. Let's see if I can do that.
Oh, I know which one that is.
So we can get this.
There's a reason for the launching machine.
Uh-oh. Let's
lost
see
our
if I
slides.
can do this. Hold on.
Astronomy in action, folks.
Yeah, Keynote crashed. I'm very sorry. Yeah, so maybe that's why the movie wasn't playing. It's okay. I'll start it up here.
So this is work that folks have done in simulating the solar system throughout its time. So the baby solar system, the planets were closer, but the movie Bryce is going to shows that the planets' orbits changed with time, and that has effects on the objects that are further out. So let's see if it'll play here. I don't think we're on the screen up there,
Yeah,
though.
it's frozen.
It's frozen. So do you want to describe it to folks? Oh,
wait,
wait, here it
yeah,
goes.
There we go.
Here it goes.
All right.
It's even on the screen behind us, so we're good.
So let's see. I don't know why it was just
Oh,
having a moment there.
It's staggered. It came. Oh, here it goes.
The MacBook's about to take off.
Yeah, it's going off the Jupiter. All right, so see if I close some apps. That will help. Yeah, I don't actually. Okay, well, let's see here. Yeah, I have no way to
It
control
contains the
slides.
entire solar system, and that crashes sometimes.
Yeah.
Solar system has crashed.
It's very appropriate.
It is. It's
Okay,
the
so let's see
chaos.
if this movie. So what's happening is that the gravitational interactions between the disk and the planets causes the planets to migrate to expand outwards. So I said that the initial configuration was about 25 AU, but Neptune is at 30 AU today. So Neptune actually migrated outwards about 5 AU, and by doing that, it basically caused the orbits of the other planets to destabilize, and that destabilization caused the dispersal of this disk of planetesimals outside the orbit of Neptune. Now, here is the challenge. Can we get it to do what I want it to do? So here we go. Yeah, so I upgraded to Tahoe, and the problem with Tahoe is that it has all this graphic stuff, which is totally superfluous and not needed, and it just slows the
RAM.
yeah, it just slows everything down.
Yeah.
So what happens when engineers get bored? They implement a bunch of features that no one asked for, which bloats the software and makes it run slow.
It's okay as long as they don't do it on Keck.
So the basic idea is Neptune moves outwards. That causes the other planets to move outwards, and that kind of destabilizes this disk of planetesimals that are further away, causing a lot of them to get flung out of the solar system. So we were the source of a whole bunch of interstellar objects for other stars. A bunch of the little planetesimals that got formed in that
Click play here.
early sequence are tossed out.
there we go.
So let's see. We're back up live. So let's see if this works now.
All right, so the effect that this has is basically if you have a, let's see if this movie will play. If you have a like a washing machine and it's going and you throw a brick in it, it basically causes it to just go haywire. And so the effect is that you disperse this disk of 20 Earth masses of trillions of objects, and 90% of it gets ejected into interstellar space, where 10% kind of hangs out in this thing called the Oort cloud, which is another topic for another time. But the main point is that 90% of this 20 Earth mass disk gets ejected into space. And if we're looking at other stars, and we're seeing this, and then we're seeing that a good portion of them could have these protoplanetary disks that form these massive rings of planetesimals, which go through this process of being ejected into interstellar space. You are basically ejecting 12 trillion objects per star, per, let's say, planetesimal forming star in the galaxy into interstellar space. So when these interstellar objects are going into the galaxy, they follow a very different trajectory than what they have when they're going around our sun, or an asteroid going around their sun. They're following these kind of spirographic trajectories because the gravity in the galaxy is very different from the gravity in our solar system. In our solar system, the gravity is dominated by the sun. The sun is the most massive object. But however, for the galaxy, you have clumps of gas, you have globular clusters, you have spiral arms. The gravitational potential is very inhomogeneous. In addition, you also have a bar. You have the bar in the center of the galaxy, which is spinning around as well. So it causes the gravitational potential to be highly variable depending on where the interstellar object is as it's floating around the galaxy. So it causes its orbit to have this kind of spirographic pattern instead of a nice orderly ellipse. And so this is actually a simulation of the galactic orbit of 3I Atlas. It has an orbital period of about 300 million years, 200 to 300 million years, where we are using the galactic potential as well as the rotation of the galactic bar at the center of the galaxy. And as you can see, for much of its time, it's going to miss our sun. It's going to miss the location of our solar system. And by the way, our sun is orbiting along with the galaxy, but I'm just plotting where its position is at this point in time at about 8.2 kiloparsecs from the center of the galaxy. And so eventually, at some point in time, the trajectory of these interstellar objects is going to intersect our sun, and that's where we have the encounter. We have the 3I Atlas coming in from interstellar space, where it was about 90 AU away from the sun 5 years ago, and several months ago in 2025, it was 4.5 AU from the sun, just inside the orbit of, just after it passed inside the orbit of Jupiter, and that's when it was detected and discovered by Larry Deneu using the Atlas telescope. So I think this is a great time to plug. We're actually going to have a live session, observing session with the Gemini telescope on Mauna Kea Observatory. That is being hosted by Shadow the Scientist, which is managed by Jamaica Marshall. And she is organizing this, so she's going to have myself, Laura May, and a Caltech graduate student who are going to be discussing in real time the observations. So far we have 150 people signed up, so I hope it's not going to get too crazy. I did ask them to invite Avi Loeb to be an audience member, just to include him. I think it would be fun to have him there, but I don't know if he'll show up. We'll see what happens.
It's the day before Thanksgiving.
So it was going to be on next Monday night, Tuesday morning, but the weather in Mauna Kea is really bad right now. So we're coming out of a winter storm, and it's starting to clear up. So we moved it to the next day, November 26th, and we'll see. We may have to readjust again depending on how the weather is. So it could be good turkey time conversation if you want to come to our observations. So the comet is coming out of solar conjunction, which means that it's in the morning side. So we're observing it right after it comes out of solar conjunction. So we'll have to observe it at 4 a.m. in the morning Hawaii time, which is 6 a.m. Pacific time. And on the East Coast, I guess we'll be competing with the Macy's parade.
The Macy's parade. Wow. So what this is, folks, if you've never heard of Shadow the Scientist, this is an opportunity to log in. It's via like a Zoom call.
It's a Zoom call.
It's a Zoom call. So you're literally watching the astronomers take data, interact with the instruments, have the telescope pointed by the person they allow to steer the telescope. The astronomers don't get to move it around. We run the instruments. But you get to eavesdrop and watch it all. And then when there's a little bit of downtime, the astronomers, if they can, will take questions and answer questions from the chat and from people. So this has been going on now for a few years, and if you follow Shadow the Scientist, you can join in.
And they don't just do astronomy,
amazing.
by the way. They do things on ships for oceanography, and it's a really amazing program. I got to attend one of the ones they did at the DKIST, so that's the largest solar telescope in the world. I was fangirling so hard. I was so excited. And yeah, you get to see, we will not be in Hawaii this time, but you get to, sometimes we are, and you know, you get to see, but we're still there, and you will see the actual screen that we see all this from. There's nothing hidden. You get to actually see what the comet looks like in the detectors, and I guess maybe it's not like this. I do want to clarify. I think people sometimes expect that they're going to see these fabulous James Webb style images with, you know, colors, and it's black and white, and sometimes it can be
it's uncalibrated. It's coming right off the instruments. You're seeing it fresh out of the instruments, so it's an amazing opportunity to join. So to me, clearly this is a comet, and it's acting like a comet, but there are some differences, and it's coming from another star. So what are some of the differences, Bryce, that we're seeing in the measurements, and what is it telling us about in the environment it came from?
Well, I mean, this is just my opinion. I don't really think there's really anything spectacularly different. So if we go back to this this plot here of the colors of 3A Atlas. So it did appear to be quite a bit red as it was coming in. This was taken right after it was discovered, before it encountered the sun or anything. And some observations taken later, and we're going to be updating this in a new paper coming out soon, shows that the comet became substantially bluer, bluer in color. So so basically in this plot, the more towards the right of the plot, the redder you are, where the more center of the plot is, the more bluer you are. And that's where all the other comets, the solar system like comets are. They're right there in the middle. And the key thing is that in those wavelengths that determine blueness or redness, you are covering areas of this spectrum where you have the emission of diatomic carbon. And I don't have the spectrum here, but before this spectrum was taken, we did not see the diatomic carbon. So the red color could be due to the fact that we did not have this additional emission of gas emission that was pumping up the bluer color, the greener color. Because when you say green, it's blue in the sense of being shorter in wavelength compared to red. And that makes, I think that was what was giving the comet the appearance of being red. The other thing is that when you're floating around in interstellar space, you have two things. You have the cosmic ray environment in interstellar space. It's very different because you're outside the heliopause. You're outside of the heliospheric environment that is projected onto the solar system by the sun that goes out to 40, 50 AU. Beyond that, the extent of the solar wind isn't as strong. So when you get out to that extent, you are affected by cosmic rays differently, galactic cosmic rays. And being in interstellar space, you're floating around well beyond any of the vicinities of the sun, of any stars, any sort of stellar environment. You have what is called a mantling effect on the surface of the comet. You have the buildup of an inactive mantle that is caused by the bombardment of cosmic rays on the surface of the comet, and this mantle appears to be red. The other effect, which was noted by a colleague of mine, Professor John Tonnery at the University of Hawaii, who is also one of the investigators with Larry Deneu. He's actually, John Tonnery is actually the principal investigator of ATLAS, but both he and Larry work together. John Tonnery says that given the high V infinity of this object, you had hydrogen atoms impacting the surface of this comet, hydrogen molecules, impacting the surface of this comet at a non-negligible energy, such that it was sufficient enough to break down some of these complex carbon molecules into kind of a reddish mush. So when we're seeing this red color, I think it's more of an effect of the interstellar, the galactic environment, rather than indicative of the environment of where it formed in its home star system. And I think once it clears out some of that material, it starts to activate, the comet's surface will resuscitate itself as it's becoming more volatilized, and due to the fact that more ice is sublimating from its surface due to the sun's heat, clearing out its surface, it will start to have a more bluer color and look more ordinary like a comet. I mean, because like we mentioned earlier, it's now, before it kind of had this kind of reddish color. I mean, this was in the very nice image that was made by Gemini. I mean, it's a false color image, but
we spoke a week or 2 weeks ago regarding this idea that the Vera Rubin Observatory, which is in Chile, has had first light but not officially functioning yet. It's doing this very expansive survey of the night sky, and there are some ideas that, oh, it's going to find hundreds of these. And could you explain why that's actually not the case?
Well, I mean,
certainly in a year's time, or the estimate of how many we'll find.
It remains to be seen. So 3i Atlas, so I'll give you a little bit of information about Atlas. It's a half-meter telescope. So it is but it's designed, it doesn't go very deep, which is a half-meter telescope, which is considered to be small, so it doesn't go very deep, but it has a very wide field of view. So it has the ability to scan the night sky very quickly and find bright things very quickly. So 3i Atlas happened to be bright enough, and it found 3i Atlas. However, the Rubin Observatory has an effective diameter of 6 meters. It's actually 8 meters, but because of some optics are blocking the mirror, its effectable use of diameter is about 6 meters. And it also has a wide field of view. So, but the point is that it has a much higher sensitivity. It can see things a much more fainter than Atlas. So what that does is, let's say Atlas is good at finding things about 2 AU from the sun, but with a much larger diameter, Rubin is able to find things, let's say 10 AU from the sun. So that increases the search volume not by a factor of 5. It increases the search volume by a factor of 125 because it's the cube. It's the cube effect. So at the rate at which we are discovering interstellar objects, we found 3 in the last 8 years. So, and that's that's assuming the same search volume. But with Rubin, if you multiply that by, so 3 every 8 years, that's like maybe 1 every 2 years. So we'll say half a year. If you increase the search volume by 100, let's say, you'll go from half a year to 50 per year. So that's why people are saying, oh, they're all very excited for this. But here's the thing, is that increase in search volume doesn't necessarily translate into increase in discoveries, because of the fact that the circumstances required to discover an object like a comet or an asteroid or an interstellar object require you to search the sky in a very particular way. We call that cadence. So cadence is like a way of describing music or dance, like a style of dance, like the rhythm and so on and so forth. Surveys also have their own rhythm or style of dance called cadence, which they use to survey the sky with a particular pattern. And the pattern used to find asteroids and comets by surveys like Atlas, because Atlas is designed to find asteroids, it's fine-tuned to find asteroids, where Rubin Observatory is a more generalized, commensurate survey. It means it has kind of a one-size-fits-all approach. And while one-size-fits-all, it doesn't fit best. So the process of finding an asteroid is actually quite a specialized thing, and the one-size-fits-all strategy that Rubin is taking is quite good at finding distant objects, like objects that are going to be beyond the orbit of Mars or beyond the orbit of Jupiter. But for near-Earth objects, or objects with anomalous motion, objects that are interstellar objects which have anomalous motion, require a different cadence where you are targeting the asteroid specifically. You basically have to look at the same part of the sky 3 or 4 times per night, so you get 4 images in one night of an asteroid, where Rubin is only going to get 2 images of an asteroid per night. And that makes, with that cadence, you can make discoveries of distant objects, but close-in objects or fast-moving objects like interstellar objects, objects which are coming from, interstellar objects seem to be coming from a very high inclination, and that's going to give them a very fast angular velocity on the sky, in the night sky. The cadence is not going to be necessarily the best at picking those up. So what it translates into, you have kind of a theoretical performance of, okay, 50, 100 per year, sure. but the actual performance might be quite a bit lower than that, based on the fact that the cadence is so much different from asteroid finding surveys.
Well, interesting. Well, folks, anybody in the audience have a question here? Yeah, over here to the right.
I have a few. This has been really fun. Thank you, guys. Okay, let's see. Where should I start? How do interstellar objects help refine our models of solar system evolution in ways that local objects can't?
Yeah, so this is a very good question. This is one that I'm very interested in. So when we discovered One-Eye Oumuamua, it was Pan-STARRS that found it, actually. Another Larry Deneu engineered thing. That was surprising, and we were like, "Wow, this is crazy! It's Rendezvous with Rama all over again." And we were like, "Okay, maybe we'll just see one. We'll just see one now, and we'll never see another one." And then a couple years later, Gennady Borisov, a guy who is an amateur astronomer, discovered Two-Eye Borisov. And they were like, "Oh, wow, this is pretty exciting. We're going to be getting more of these things." And then there's this kind of this drought, 5-year drought between Two-Eye Borisov and Three-Eye Atlas. So in that time frame, the science for interstellar objects was very speculative. And it was not, it wasn't really, it was interesting, but we weren't finding them very often. So we were kind of wondering, okay, what can you really say about the formation of planetesimals around other stars based on two objects? But now, lo and behold, we have a third one. And we have this new survey coming online, which, may or may not find. We'll see how it goes. It depends on the software that they have to develop. It may have the ability to find more of these at a substantial rate in the future. This gives us the possibilities that with greater number of statistics, we're going to have more information about the planetesimals forming around other stars. So it starts to become exciting because we can observe exoplanetary systems indirectly, or let's say quasi-indirectly. We can observe planets like jiggling by the jiggle that they cause on the star using the radial velocity method, or the dimming that they cause when they transit in front of them, or in very, very lucky circumstances, direct imaging. You can see a planet, or in this case, like these protoplanetary disks, you can see this broad coverage thing, but we don't have the ability to observe an asteroid around another star. They're very, very tiny, way too faint, and the stars of the orbit are way too bright that they would drown out any light from an asteroid. So now it starts to become kind of exciting that, wow, we have the ability to sample the macroscopic bodies that formed around another star. And the reason why that's interesting, the reason why that's important, is because there's now a mountain load of evidence out there from all the architectures that is evident from all the exoplanet research that's been going on by the radial velocity surveys and by Kepler and TESS and WASP and all these other fantastic things. And now you start to have ALMA showing us all these plethora of all these protoplanetary disks. We see that the configurations that we're seeing around these other exoplanetary systems is quite different from our star system. Almost in a way that we could say that, wow, maybe the solar system is not the typical case for the outcome of the planetary formation process. So for example, we think that all the planetesimals formed within 40 AU. They had an inner edge at 25 AU, but they didn't go out very far beyond 40 AU. So that kind of limits the kind of chemistry that can occur that can influence their contents and compositions. But like in this case, this ALMA HL tau, it is very much more extended. It goes out well beyond 40 AU. It goes up to like 100 AU. We also see there's also a system called HR8799, which is a directly imaged exoplanetary system, which shows evidence of a debris disk beyond 100 AU. And beyond 100 AU, you can have very exotic chemistries that occur, very exotic ices. One of it is called dinitrogen. And that is something, dinitrogen ice is something we only see on the very largest of the Kuiper Belt objects, like the Plutos, the Irises, and so on and so forth. And for objects that are much smaller, we don't have that. It was basically everything formed too close to the sun, and you couldn't have this. You could not have a nitrogen-rich composition because all that ice would have been too hot for it to solidify into ice. But in a system like HL Tau or HR 8799, those planetesimals could have nitrogen or other very exotic materials. And so I don't think it's going to necessarily inform us on how we better understand the planetary formation in our star system, but it's going to give us a more holistic view, more complete information of all the outcomes, from the planets to the asteroids to the comets. From our star system, we have a really good sampling of that, but for other star systems, we don't. And so I'm blubbling on here, but there was one thing I realized I was driving all along the line here, and this plot also kind of shows us here. So this right side right here is a computer simulation. So this is what we think is going around other stars. But we can't see that. All we can do is use the laws of physics and try to create a scenario that seems feasible. And these simulations are calibrated on the information from our star system. We actually use the observed properties of asteroids and comets in our star system to calibrate these formation models. So it's kind of weird. So we're doing something in a computer to try to say something about what's going around another star, but also using stuff from our star system to calibrate that to really inform what's going on. But the interstellar objects are going to give us direct, observable constraints on that we've never had before. So it's going to be very exciting.
So before we get to any of your follow-ups, let's see if anybody else in the audience has any questions. So up in the back, yeah.
Hey.
So is there, I mean, when we're looking at the trajectories of these interstellar objects, it seems like it's a very simple. You don't see, you only have like a basic path where it's coming in and bouncing in. Like, are we assuming that these objects are basically monogamous to our sun, and rather than, are they bouncing off other stars also? I mean, is there any?
Well, that's a very good question there. So that was one of the big things that we asked Oumuamua when we first saw Oumuamua. Did Oumuamua see other stars? Because that had a very strange shape. It was inactive. So we're like, okay, what happened to this thing? Why isn't it like a comet? Why didn't it grow a tail? Could it had some weird encounter floating around in the galaxy, like with a supernova or another star that bungled it up before it came into our star system? Now the thing is that the crossing time, the disk crossing time in our galaxy is like billions of years, meaning that the time it takes for some object floating around, free-floating object to go around our galaxy before it encounters another star is like 1 billion years. So it's very highly unlikely that Oumuamua or these other interstellar objects had encountered another star before they encountered ours. This could change in the future. Yeah. So that's one of the unknown unknowns that's going to be coming out into Rubin, is finding an interstellar. There's going to be two. Finding an interstellar object, one that is nitrogen rich, like we mentioned before, the exotic chemistry stuff, but also one that says something about the history of the galactic environment experienced by this object. Could it be enriched in some weird metals or something that had to have only come from a supernova? Like, did it fly through like a cloud of gold or something? That's awesome. So I mean, it's just but I mean, it's so yes. So in a sense, yes, they are monogamous, right? But this could change in the future. We could get very lucky and see something where it did encounter some other star, some other significant environment other than interstellar space.
Then we have time for one more question. We can come back to you if you want to ask one more. I don't think there's. Yeah, let's come back to you, ma'am. You said you had multiple ones. Do you want to ask one more, and then we'll think Bryce.
It's about eccentricity, and the trajectory. And I know you mentioned that if it doesn't encounter a gaseous planet, it couldn't gain speed. Or is that right? Did I get that correctly?
Become excited.
Yeah. You could not explain what it means is that you couldn't explain the high eccentricity as being the result from a low eccentricity object, like a comet with an eccentricity of less than 1, which originates from the star system.
Right.
That had its eccentricity increased to above 1 due to the encounter with one of the gas giants. And this actually has kind of a historical relevance, because the topic of interstellar objects is actually quite old. It's actually hundreds of years old. Because the very first comets that were discovered, and you have Halley, which is a periodic comet. But after that, most of the comets which were discovered were non-periodic, that they had orbital eccentricities of about 1. So they're coming in and flying out, never to be seen again. And what people were wondering is that, okay, these objects were about 1. Could they be from other stars? Could they not be bound to the solar system? Could they actually be hyperbolic? Because they didn't have the techniques, the instrumentation that was precise enough back then to determine the orbits to well enough, let's say, precision that could distinguish between it being something as hyperbolic or parabolic. So the question was, it's like, okay, is this something which originates from outside the solar system, or is it something that is being, let's say, being excited by due to gravitational perturbations by the other planets? Because they knew how gravity worked. They had perturbation theory back then. Laplace did that. You know, Laplace and other French scientists did this. This is actually Virginia Trimble. She told me about this. So,
oh, really?
Yeah. She has. So I mentioned Avi Loeb, another person who has a very profound knowledge of astrophysics and talking about broad is Virginia Trimble, who is a professor at Irvine.
Irvine.
And I think she's going to be a speaker at LA.
So I'm hoping we'll see.
Sorry, I should have said something. But no, she's a national treasure.
She really is.
Yeah, she is.
And, you know, she's brilliant, and
she has a great book that you gifted me on women astronomers and their own words as well, compounding some of the amazing history also of, you know, not just modern astronomers, but past astronomers. She's an amazing historian, astronomer, everything. Yeah.
Yeah. Well, let's thank our speaker again.
Thank you so
Bryce,
much, Bryce.
thank you so much for joining us tonight. Appreciate it. And folks, make sure you sign up for Shadow the Scientist. Come in and watch next week and eavesdrop on their observing run and see the data as it comes right off the telescope. Once again, I want to thank all of you for joining us. We went a little long tonight, but I think it was worth it to hear about 3i Atlas and these interstellar objects. It was just fascinating. But we will be back next month, of course, with All Space Considered, that's brought to you by Griffith Observatory, the Department of Recreation and Parks at the City of Los Angeles. And as always, we like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. So we'll see everybody next month. Thank you all very much.
Thank you.